Imagine being able to literally smell a dangerous drop in someone's blood sugar, or like not realizing you've bitten your own tongue until you actually see the blood.
I mean, it sounds like complete science fiction, but it really is just a question of biological hardware.
Yeah.
We prioritize vision and hearing so much that we completely take the rest of this invisible machinery for granted.
Right, exactly. So today's deep dive is into those other senses, the chemical and physical ones that secretly build our reality. And while I'll step into the student role today and you can be the lecturer, we're pulling from section 5.5 of chapter 5 from Psychology 2E to figure out how our bodies decode this invisible world.
I will gladly play the lecturer today. Let's start with the chemical senses. So taste and smell, they're called chemical because the receptors literally respond to molecules in your food and the air.
Right. So jumping into section 5.5, I mean, we all know that old elementary school tongue map is a total myth, but the textbook points to some new evidence for a sixth receptor, like specifically for fat.
Yeah, exactly. Alongside umami, which is that savory MSG-linked flavor, fat is really emerging as its own distinct taste.
Oh, wow.
Yeah, what's actually happening is molecules from your food physically bind to receptors on your taste buds. And by the way, if you ever worry about permanently ruining those by burning your tongue on hot coffee, don't.
Oh, thank goodness.
Right, these little cell groupings regenerate every 10 to 14 days.
Okay, so they're highly resilient. But taste is deeply intertwined with smell, and this is where I want to ask you about the text. The textbook notes humans have fewer than 400 functional olfactory genes, while dogs have between 800 and 1,200.
That's right.
Does that just mean, like, smells are louder for dogs?
Well, no, not just louder. It means dogs are detecting an entirely different spectrum of chemical reality.
Like a whole different world.
Exactly. Those extra genes let them pick up on minute chemical signatures we just don't have the hardware to perceive, like specific volatile compounds from cancerous tumors or sudden shifts in blood glucose.
So it's not volume, it's more like we're looking at a black and white TV and they're seeing in full color.
That is a great way to put it.
And these chemical signals go beyond just food or disease, right? Like, what about pheromones?
Ah, right. So in animals, like rats, pheromonal communication is undeniably clear. It triggers very specific reproductive or territorial behaviors.
What about in humans?
It remains heavily debated, honestly. We just don't have conclusive evidence that human behavior is driven by invisible chemical messages in that same way.
That's wild. Just a physical molecule binding to a receptor constructs flavor or communication. But our body doesn't just interpret chemistry, it interprets physical force too, which sometimes means literal tissue damage. So let's talk about touch and pain.
Right. Pain isn't just one single thing. The textbook draws a sharp line between inflammatory pain and neuropathic pain.
Okay, what's the difference?
Well, inflammatory pain signals actual tissue damage. You touch a hot stove, your tissue is damaged, and the pain tells you to pull away.
So it's a functioning fire alarm, but neuropathic pain feels different, right? Like a wire stripped of its insulation, sparking and sending false fire signals when there's no heat at all.
That's a perfect analogy. In neuropathic pain, the damage is to the neurons in your nervous system. The alarm system itself is broken.
You know, I was thinking it's easy to wish we didn't feel pain at all, but Section 5.5 talks about congenital insensitivity to pain.
Yeah, that genetic disorder.
Right, where people feel pressure but no pain. Without that alarm, they suffer horrific injuries, like literally biting right through their own tongues and face way shorter life expectancies.
Precisely. Pain maps our physical boundaries against external threats. But we also have to map our internal physical awareness. Think about it. How do you know where your limbs are right now without looking at them?
I mean, it's the vestibular system, right? But help me out here, lecturer. I know it's in the inner ear next to the cochlea, but how does fluid inside my head know what my legs are doing?
Think of the fluid-filled organs in your inner ear as a biological carpenter's level.
Oh.
Yeah, when you tilt your head, fluid shifts and physically bends these tiny hair cells inside the organs.
And that tells the brain we're moving.
Exactly. That mechanical bending gets translated into an electrical signal that your brain reads as gravity or motion.
So my inner ear is a gyroscope. But it doesn't work alone, does it? It combines with proprioception, which is our perception of body position, and kinesthesia, our perception of movement.
You've got it. Your brain fuses that gyroscope data with continuous signals from stretch receptors in your muscles and joints. It's constantly calculating limb tension to keep you upright.
So for you listening, next time you eat pizza, just appreciate the massive hidden processing going on. You're tasting umami, feeling the heat so you don't burn those regenerating taste buds, and your inner ear's carpenter level is working with your stretch receptors so you don't fall off your chair.
It's an incredibly complex system. And, well, it leaves you with an interesting thought. If dogs experience a vastly richer chemical world just by having a few hundred more olfactory genes, how much of the real universe are you completely blind to simply because humans lack the sensory receptors to detect it?